Hi everyone, thank you for having me today. Really happy to be at PCMI again. I'm Angèle Taillard. Now I'm a postdoc working with Asuncion Fuentes team on the Cell for Life ERC. And this ERC has a goal, which is to find sulfur in any kind of forms at this point. And I will present today if we have any hopes to detect it, S-bearing species with the GEMS web. So let's start with the missing sulfur problem. So many of you might be aware that this is a long time problem. Sulfur is the 10th most abundant element in the universe. And we know that chemistry-wise, it has an important role. So small molecules such as H2S and others can play as catalysts on the surfaces and create bigger molecules. However, as Edward Jenkins has described sulfur, as a troublesome element in his very famous studies on the gas phase depletion, we have still doubts on what happens to the sulfur between the H2 regions and the tallest cores. We have we have observations of comets now that give us a hint on the fact that sulfur is somewhere in between. But when it comes to the sulfur depletions, there are several orders of magnitude of uncertainties on the abundances of sulfur. So most of you must be aware that we detect sulfur in many, many molecules in the gas phase. But if we take as an idea the cosmic abundance of sulfur that Edward Jenkins has defined, these molecules and the others will represent only less than 1% of the cosmic abundance of sulfur. So the question is, where is the rest? And as I mentioned, comets give us a hint on what could be processed during the star formation. And we had this in situ observations with Rosetta on 67P comet. And we have a lot of measurements of molecules that comes from the coma. And it's important because it's photodesorbed product. So it means it might be fragments of something bigger on the surface. But what it tells us is that we have a lot of H2S and sulfur in its atomic form. The rest is distributed in smaller molecules. And you see, even in this order, we have chains of sulfur. So it's important for us to keep this in mind because it's informs us in what kind of molecules we could expect in earlier phases. So what about chemical models? What do they give us as hints? There are two studies that, the first one is from Navarro Almeida in 2020, and the second one is from Las Casali in 2019. And they really conducted a big study of the sulfur and its chemical network. They updated a lot of things that were missing, a lot of data from the lab and other things in the network. And they arrived to the same conclusions that more than 95% of the sulfur in the cold dense regions is locked in the ices, which is a bit accurate considering that we detect only 1% in the gas phase. So depending on the initial parameters that you put in your model, the two main reservoirs comes to be H2S and SO with OCS that is coming, and depending really on the initial parameters. So the H2S is quite a good news because we are expecting it in the comets as well. So it means maybe it's formed very earlier in the dense core for phase, and then it can be reprocessed or kept in this form until the comets. So what about the ice detection so far? Because we're looking for 95% of it locked in the ices. Well, this is where it starts to get a bit depressing, as that up to this date, we only have detected 2 molecules with only 1 solidly detected. So in 1995, Elisabetta Palumbo and her team detected OCS vibrational band around 5 microns, which we were hopeful to get some others, but we had to wait until very recently, this year with the James Webb Telescope, for tentatively detection of SO2 in ERAS-2A, which is an ISO. So if we take the abundances derived for these 2 molecules, this would only account for 5% of the cosmic sulfur abundance. So we're missing more than 90% of it. So where is the rest, and can James Webb give us more information on it? because now that we have this huge telescope with a very big sensitivity and spectral resolution, we are hopeful to find a sulfur. Okay, so that's why we had this project going. And before I start with what we did, I will show you what reservoirs we're looking for with the JWST web. So the first molecules we have identified are the one that I showed you in the chemical models, which are simple molecules. We have CS2, OCS, H2S, and SO2. We want to be sure that OCS and SO2 can be detected in any phase of the star formation. But we have also an interesting form of sulfur, which is the allotropes. And allotropes are basically the sulfur chains. And you see that there are plenty of options. And according to Stephanie Scazzo and her team in 2022, one of the forms that sulfur could come into is S8. So this means we would have the hypothesis that we would have a very early depletion of sulfur that will form these molecules, and then it will be kept in the ices until it's being reprocessed during the star formation. And then very recently, but this is an idea that's been in the community for a long time, are salts. There are two studies that came out last month, which are studying the vibrational contribution of salts in the JWST web wavelength, but I will not talk about the salts today. That's something that will come much later. We're just getting this new lab data on salts, so we will go on it later. So about these two kind of reservoirs, what did we do? Well, first, in order to be sure that we detect them in the JWST web, we have to make sure that they are present on the spectral wavelengths of the JWST web, right? So we compiled all the available band parameters from literature and made sure that most of these molecules were could be detected on the wavelength. And it's the case for many of them, but the other difficulties is we need to have the laboratory spectra to make sure that we identify them well and that we have the band parameters. So my team has derived a new spectra for S8, which is around 21.3 microns. It's detectable with MIRI. And we also have a new spectra for CS2, which is the main vibrational band is around 6.6 microns. So then we made sure that the OCS, SO2, and H2S were also detectable, which is the case with the JWST. And we could carry on our experiment. So in order to test for the detectability of these molecules, we used a code that I started developing during my thesis, which is a synthetic ice spectra generator. So it's making synthetic observations on very simple approximations, which is that each vibrational mode in infrared could be represented by a Gaussian or a series of Gaussians. So for example, you have here the H2, I'm sorry, it's very small, but you can see that we fit a few Gaussians over a laboratory spectra in blue. And we obtain the band parameters of these Gaussians and we put them in SynSci-Spec, meaning that to get the intensity of your band, you have to input a column density yourself, which then will give you the intensity of your new band. And then as the user, you can choose whichever molecule's column density you want to input in the code. And then it gives you this black spectra, which is the sum of all the components. So it gives you an idea of where the components you're looking for are, what's intensity, and you can really play around and give whichever ice composition you want and study, help you study either your ice observations or just simply see if molecules could be detectable or not. So infrared observations are very complicated, and something that is playing a huge role in the analysis is the fact that when you take a vibrational spectra of a pure species, the band will be positioned at certain positions. And the problem is that if you add any molecules inside your chamber, you will obtain like mixing effects, which is the interaction between the vibrational groups of all of your molecules. And then you get shift in positions, shift in the, the shape of your band can change. The many other things can happen, like appear, like new vibrational modes, for example. And so to make sure that we would detect all of our molecules, we did a very simple test, as that we took the main species in the ices, so H2O, methanol, CO2, and CO. And we added our sulfur species inside, and we just wanted to see with what species could it be overlapped with. So we added this mixing mixture, and we derived the new band parameters. And from these new band parameters, we could get like this spectra that I show you. So they are, this one is, for the sake of clarity, it's on the near spec observing wavelength, and this is on one of the part of the MIRI wavelength. So what happens is that, as you can see, as I mentioned, sorry, some vibrational modes are overlapping with each other. So for example, this is the water band overlapping with the methanol band. You have CO2 and CO, which are quite isolated, but you see here, if we zoom, we have a bit of a problem, which is only showing you the difficulty of detecting sulfur species. You have here the main vibrational band of H2S, and there is a tiny contribution here from the libration mode of methanol. And we suspect that this is one of the reasons we are not detecting H2S so far, and we have other things that I will mention later. But as you can see, this molecule is covered by another band. And if we look at the others, for example, CS2 here, this band here is covered by the two bending modes of water and methanol. So if CS2 is not present in high quantities in ices, it will be overlapped and not detected. In this example, SO2 band that you see here is very isolated. It is not the case in a realistic approach. There are many other molecules that should be added around it, but this was just simply to test where were the bands. So now what we do is that we will add a few more molecules, and we also be adding noise. That is based on real observations from Macular et al. Observations of Chameleon 1. And we will create synthetic spectra. So what we do is we take 3 different science cases that were derived from Bogert et al. 2015 in 3 different environments. So you see we have the dense cloud, the LISO, and the MESO. And for each, we have column densities that we will put in our model. So you can see that for these molecules, in particular, this is not very accurate because now we know that there have been detection of all of this. So our spectra will be much simpler than that could be in reality. But this is simply to see how much the ice composition could affect the detection of sulfur. So what we do is we input these column densities I showed you, and we change the flux on which we want to observe. So in this case, we take a 1 milligensky flux, which is, we only use a simple flat continuum. It's not realistic. In reality, continuum contributes a lot to the analysis, but we wanted to keep it simple. And you have in black the spectra without the sulfur molecules. And we iteratively add column densities of each of these species in here, and we see at what point we reach the 5 sigma detection. So in the case of 1 milligensky, we have a very high signal to noise ratio. So the column density that we derive are very low. So this gives us hope for detection. But in reality, since the GEMS web is so powerful, we can start to probe deeper and deeper line of sights. And here you have the flux divided by 10. And sorry, you start to see that the signal over noise ratio is decreasing, and we start to have to add, we need to a lot more column densities with respect to water to really be able to detect. I will show you the values right after. And it's even, if we go even deeper to a flux divided by 25, we have the signal to noise ratio becomes to be exponentially low, and the column densities that we need for the detection starts to be lower and lower. Oh God, okay. So if I show you the 5 sigma detection threshold that we derived, you can see that with a decreasing flux, the column density that we need for the detection is increasing. Realistically, this at 1 milligensky could be achieved in many of the chemical environment that we're studying. But as we go deeper and deeper, they start to be very difficult to consider it realistic to obtain these values. We will need a lot of favoring conditions, which we don't think could be achievable unless we have an alignment of the stars. So what I did not mention is that despite these column densities that could be optically, we could maybe obtain them. My model has a lot of limitations, starting with the fact that we are not including many physical aspects. The first one being the ice processing and scattering, which plays a big role in the detection of H2S. So you have a red ring of water that appears because of the scattering, which is not included in the model, which would make H2S detection difficult. Then in this study in particular, I didn't add photospheric lines, which is very hard for identification of lines. We also have crowded area, and since iSpec is a database that I do alone at the moment, there are a lot of missing molecules, and also it's very hard to be sure that these molecules could be detected in these crowded areas. And then finally, now we have very recent studies, such as the one of Emmanuel Dartois in 2024. We know that we are expecting grain growth to be much more important than we actually thought it was. So I'll come back to allotropes very quickly. Remember that this was one of our hopes, is that sulfur might be in this form. So I added the S8 in my model. And in black, you have the spectra without the sulfur, obviously. And in red, here, that you can barely see, this is what the band would look like if I take all of the sulfur, and that I put it inside one single grain, and you see that even with the cosmic abundance of sulfur, we are not detecting S8. We would need 10 times this value to actually be able to detect S8 with a 5 sigma detection. So what does it mean? Well, you understand that maybe the detection of sulfur species in ice is going to be compromised for a while, unless, of course, all of the models are wrong, which I would happily be proven wrong. And the hypothesis one that we had is that sulfur was locked in allotropes. And as I showed you, the vibrational bands are way too low to give us an insight of how much is there in the allotropes. And the hypothesis too is that maybe sulfur is so well distributed in the ices that the fact that the band strengths are so low for each of the species makes it hard to detect. And there might not be a main ice reservoir sulfur, but because we would have already detected it. However, there's still some species that are left to identify and study, which are salts, as I mentioned, maybe other allotropes that we don't have the band parameters yet, and ions that could come in the gas phase and give us information on the precursors in the ices. So it's probably a mix of all of this, and I conclude on the fact that probably these detections are very hard with the GEMS web. I would like to thank everyone and PCMI for this great conference, and of course the ERC for having my postdoc going. Thank you very much for your attention, and I'll be happy to answer any questions. Thank you.